Here's some wonderful advice from the dashing 3 cadets. Just around the corner, there's a rainbow in the sky. So let's have another cup of coffee, and let's have another piece of pie. Trouble's just a bubble, and the clouds will soon roll by. So let's have another cup of coffee, and let's have another piece of pie.
Okay, we'll move to our last video lecture on the chapter on thermochemistry. And here we will talk about calorimetry, and we'll feature the coffee cup calorimeter. Now, why do we do calorimetry? What's this all about? Calorimetry is an experimental way of measuring heat effects, especially the heat that's absorbed or liberated in a chemical reaction or a phase change. You might ask, well, okay, why do we want to know these heat effects or these enthalpy changes? It turns out that the enthalpy change for a reaction will describe for us, and we'll learn this later on, it'll describe for us the temperature dependence of a chemical equilibrium. We haven't talked about equilibria yet, so we'll just have to wait for a while. But needless to say, we chemists, we scientists, have a need to determine the enthalpy change for various reactions and phase changes. Now, one way we can estimate these is through the use of delta H's of formation and employing Hess's law if we have other known enthalpy changes that are given to us. But let's say we have a reaction for which we have no tables, no data, but we want to be able to experimentally determine the enthalpy change. Well, to do this, we use the method called calorimetry. And there are two basic types of calorimeters. One is called a constant volume calorimeter, and the other is called a constant pressure calorimeter. A constant volume calorimeter sometimes is also called a bomb. Be careful, can't say that everywhere, but is oftentimes called a bomb calorimeter, where the reaction takes place in a container which has a lid that's tightly closed. Think something like a pressure cooker if you've been in a kitchen and you know what a pressure cooker is, where you tighten down a lid so that when the reaction takes place, the volume remains constant, but it's possible that the pressure inside that calorimeter can change dramatically. And in fact, if there's a gas produced in the reaction, then the pressure inside can go up dramatically. Now, I won't focus on a constant volume calorimeter. You can look in the textbook and see examples and see problems involving a constant volume calorimeter. Instead, I'll focus on the constant pressure calorimeter, which is a little bit easier conceptually. And this constant pressure calorimeter is something that we call a coffee cup calorimeter for reasons that will become obvious. Now, the condition of constant pressure is actually more common to us because most chemical reactions that we deal with do not occur in these pressure cookers, these constant volume contraptions. Most of the time when a chemical reaction takes place, it's at 1 atmosphere pressure, and we don't have tightly screwed on lids in a constant volume, iron-tight container of any sort. So here's a depiction of a coffee cup calorimeter, and it's as the name implies. It can be nothing more than a styrofoam cup in which we initiate a reaction in some way. This can be initiated by either just mixing two solutions together in a coffee cup calorimeter. The two solutions that we mix would initially be at the same temperature, as we will see in a second. Or perhaps we initiate the reaction in some other way by perhaps breaking a vial so that now a reactant that was in that small vial becomes exposed to the rest of the solution. And the reaction in a coffee cup calorimeter usually takes place in an aqueous environment, that is a solution where the solvent is typically water. And so we're thinking about our aqueous-based types of chemistry: acid-base reactions, precipitation reactions, some redox reactions, reactions of this sort. Now, because the reaction takes place in a styrofoam cup or an insulated system, thermal energy does not pass between the system and the surrounding. Consequently, if a reaction releases thermal energy, because the thermal energy cannot be released to the surrounding, the thermal energy increases the temperature of the solvent. Again, the solvent usually being water. So that we monitor the progression of a reaction by looking at the increase in temperature of the water, the solvent, in the coffee cup calorimeter. Here's an example problem in which we initiate a reaction in a coffee cup calorimeter by mixing a certain volume of a certain molarity of something like silver nitrate in this case 0.05 liters or 50 milliliters, of a 0.10 molar solution of silver nitrate, and we mix this with an equal volume, 50 milliliters or 0.05 liters, of a 0.10 molar hydrochloric acid solution. Now, what kind of reaction is this? Well, let's think. Silver nitrate is a soluble salt. Hydrochloric acid is an acid, but everything is soluble. But if we have an exchange reaction, we can form silver chloride, which is a insoluble solid. That is, this will be a precipitation reaction. So the net ionic reaction in this case would be silver plus cation plus chloride minus anion reacting to form silver chloride, the insoluble ionic compound. All right. So let's say that we initiate a reaction of this sort by mixing together 50 milliliters of silver nitrate with 50 milliliters of hydrochloric acid. Initially, both of these solutions being at the same temperature. Let's say they were 23.40 degrees centigrade when we mixed them together. And after the reaction occurs, yes, a precipitate will form, but after the reaction occurs, we measure the temperature of the aqueous solution and find that the temperature has gone up from 23.40 to 24.21 degrees centigrade. Or in other words, there's an increase in temperature of 0.81 degrees centigrade. Why did we have this increase in temperature? Because the reaction must have been exothermic, releasing thermal energy, that thermal energy resulting in an increase in the temperature of the aqueous solvent. It's basically a heat capacity change then. But also, before going to the next slide, let's note which of the reactants, if either, is the limiting reactant. Well, it turns out, in this case, by the way we designed this experiment, we would have 0.005 moles of each reactant. So each one is equally limiting. Just remember that the number of moles of limiting reactant is 0.005, and we'll see that we need that in the next slide. Now, from that delta T, that 0.081 degrees increase in temperature, we can calculate the thermal energy that has been released from the chemical reaction to the aqueous solvent. We plug that into the equation for the specific heat of water, and we've rearranged that equation to solve for Q. Q is equal to the specific heat of water times the mass of water times that delta T. Now, the specific heat capacity of water, we know that value. That's 4.184 joules per gram per degree Kelvin. What's the mass of the water? Well, let's think. We mixed 50 milliliters with 50 milliliters, mix them together. We should then have 100 milliliters of water. We know the density of water, and even though there are solutes dissolved in these two aqueous solutions, essentially the density of water we can assume to be 1. So we know that the density of water is 1 gram per milliliter. So we had 100 grams of water. So that's the mass in this equation. And the delta T is 0.081 degrees Kelvin, or degrees centigrade, because the step size for Celsius and Kelvin are the same. And we get a value of 338.9 joules. Now, one of the reasons we did that problem involving the horseshoe, the heated horseshoe, and then transferring thermal energy to the bucket of water is because, remember that problem that we did earlier? Because we wanted to emphasize the concept that in an isolated system, energy is neither created nor destroyed. It's just transferred from one place to another. In this case, the thermal energy being transferred from the hot horseshoe to the colder water, right? Well, in this case, the energy that is released in the reaction is transferred to the water, so that we can say that Q1 plus Q2 is equal to 0. That energy is neither created nor destroyed, it's just moved around. Now, Q1 and Q2, we can define either one of these as the reaction and the solvent. Let's say that in this case, Q1 is a solvent, and that Q2 is the thermal energy released by the reaction. So Q1 plus Q2 is equal to 0, or in other words, Q1 equals minus Q2. So using the information we have for the specific heat of water and the increase in temperature of that 100 milliliters of water, we're identifying that amount of thermal energy as minus the Q reaction, minus the thermal energy released by the reaction. So remember that number was 338.9, so if we put the minus sign in front of it, we have minus Q of the reaction is equal to 338.9, or in other words, Q reaction is equal to minus 338.9. Okay, now a delta H of reaction, Delta H's are just Q's, thermal energy, divided by the number of moles. In this case, the number of moles of the limiting reactant. Okay, well, the Q of the reaction we just determined to be minus 338.9 joules. Okay, the number of moles of the limiting reactant, 0.005 moles. So we get the delta H of the reaction as being equal to minus 67.783. I mean, there's probably too many significant figures here. Minus 68 or so kilojoules per mole. So this is an exothermic reaction. And of course, the fact that the temperature of the water increased by 0.81 degrees when we initiated the reactions was a giveaway. It told us that this must be an exothermic reaction. So that's an example of how we can experimentally determine enthalpy changes for reactions using a coffee cup calorimeter. Okay? So that's the end of our video lessons on the chapter on thermochemistry.